What are topological insulators? Let's start with the quantum Wall effect. So when we have 2D free electron material and we apply a strong magnetic field and an electric field, due to the Lorentz force, our electrons are going to have this circular behavior. So in the bulk, our electrons are going to be localized, meaning that we have an insulating material. What happens in the edges? So due to the incomplete circular movement, our electrons are going to flow along the edges, creating this current. So if we take a look at the band structure, the solution for this system is the Landau levels. So we have the Fermi level in the middle of the bands, we have an energy gap, so we have an insulating material. But we also have conductive edge states along the edges. So let's take a look at the edge of the band structure. So due to these potential barriers in the edges of the material, the bands will cross the Fermi level, creating these edge states that can conduct electricity. And this current is quantized, meaning that we have a quantized conductivity, depending only of this topological invariant, which is the share number, depending of the number of channels that we have. And it is topological because even if we deform the material or the edge states are going to still be there, or if we put impurities in the bulk of the material, it will not influence these currents. So it is topological, keeps the properties under smooth perturbations. But this is very promising for applications. What's the but? It requires strong magnetic field and low temperatures. So now we ask, is this the only system that presents a topological invariant? The answer is no. We have these amazing topological insulators that doesn't require magnetic fields. Due to the spin-orbit coupling that some heavy elements has, meaning that we have a band inversion creating these edge states that we have in some materials. These edge states are spin texture, meaning that spin up comes in one direction and spin down goes to the other direction. And even if we have current going in different directions, this is possible because due to the protection of time reversal symmetry, an electron cannot interact with the other if they have opposite spin, because this will break the symmetry of the system. So we have helical edge states. And now we were talking about 2D topological insulators, we can evolve to another dimension, 3D topological insulators, and instead of edge states, we now have surface states, and instead of helical edge states, we have a spin momentum locked, meaning that the electron spin will be dependent of its momentum. So in my PhD project, I work with this bismuth selenide, which is a 3D topological insulator, has these topological properties that I was talking about. I work with a molecular beam epoxy to grow this good quality bismuth selenide. And this is for very promising materials because we have a lot of applications in low dissipation of energy, spintronics, and also topological quantum computation. Contact me for future collaborations.